Okay, so let's see what this looks like. You're going to see a lot of grinding wheels. You're going to see a lot of potter's wheels and bicycles and merry-go-rounds. So you'll see those for quite a bit in the next couple weeks. In this one, I have a grinding wheel, and it's starting from rest. I know, let's see, it has constant acceleration, and it ends or turns at a rate of 250 revolutions per minute. So we want the angular acceleration, and we want the theta. So that would be the angle through which the drill has rotated. Theta. It's a lot of words for one simple little symbol. So what did I do? I started off with some of the tools that I gave you in 161, or that you have seen in 161. And it's just kind of making a list of what I've been given. So if I'm starting from rest, then my omega naught, my theta naught, they're both 0. So that's just my x naught equals 0, my theta naught equals 0. I have this omega. I wrote it as omega, but I really actually need to be careful here, because omega needs to be in terms of radians. So I can write this in terms of omega, but just remind myself that I need to do a conversion. So do something to remind yourself to do something with that. Revolutions per minute won't do the math for you. We know how long it took us to get there, and we want our alpha. So you can see the first thing I did, as I said, okay, let's define this quantity, and you're going to use this conversion a lot. What does this say? It says, here's my wheel, and what am I going to do? From here, this would be like 0 radians. If I go all the way around and back, well, this is 2 pi. So there's 2 pi radians per 1 revolution. And I know how many revolutions per minute I have. Then the other trick here is, while you'll see a lot of revolutions per minute, we don't do that in physics. That still is per seconds, meters, kilometers, or meters, kilograms, and seconds. So we've converted it here. My omega, my angular speed, is actually 26 radians per second. So pause, come back, and tell me how you went about getting your alpha. So I look at this. I'm like, okay, I have a change in omega, and I have the amount of time. So my alpha is just the same as acceleration is, right? We're just looking at the change in our omega. So my omega final is this 26 radians per second, minus my omega initial, which is 0, divided by the amount of time. Well, this is this 3 seconds. So what do I get? 9, 8 and 2/3. Yeah, checking my math. 8 and 2/3 radians, oops, and this is seconds, radians per second squared. Cool. The angle through which the wheel has rotated. So now let's think about what we have. We know our initial, we know our final, we know our alpha, we know theta naught is 0. See, what else do we have? I actually have everything. The only one that won't get me to my theta is the top one. And then I look at that, and now it's a decision time. What do I have to do here? Well, this just gives me a final answer. This would be 0. This would be 0. We've just solved for alpha, so this is just doing then a straightforward step of going 1/2, whoops, the magic E, Y, E-Y, times 8 and 2/3. Oh, hey, look at that. Radians per second squared. And then times my time squared of, what did I say? So 399 seconds. Squared. Yes. Oh, yeah. I already squared my 9. Okay. Let me stop doing things in my head so I don't mess you up any more than I just messed my own self up. So 3 seconds squared is 9 seconds squared. Why was I freaking out about that? My units, they got to cancel. So it's kind of handy. 2 on top, 2 on the bottom. So I get, that cancels. So 72 thirds radians. Now I'm doing math in my head, which is always dangerous, so double check my work, but the mechanics apply. And I will double check when I'm done here. All right, so let's make it a little harder. I have a coin. This one has, you're given the radius of the coin. Let's see, 0.024 meters, and it's dropped from the edge, or dropped on edge, and you try that, it's not as easy as it sounds, onto a horizontal surface, and it rolls. And so you're given the initial angular speed of it, and it rolls in a straight line without slipping. You are going to see this without slipping a ton. And right now, all I want you to do is just kind of file it away into the back of your head, because we're going to explicitly talk about that when we talk about energy and kind of relating things together and why that's important. But kind of the end of the story, the moral of the story, the giving away the surprise, if it's slipping, it's just sliding. There's no rotation. So we need to roll without slipping in order to have rotation. How's that? So we have to have some sort of friction is the gist there. So again, I made my list. Here I went ahead and defined alpha as being negative. So what have I said? What I'm saying there is that my tangential velocity is going that way. And see, so I'm rotating. How am I going to rotate? I'm rotating like this. Yeah, there we go. Rotating like this. So therefore my angular acceleration is going to be going this way. It's slowing it down. So there's my alpha, and this would be my omega, and there's my tangential velocity. Let me make that clear. Cool. So we know what alpha is. It's slowing it down at 1.9 radians per second. Let's see, we know our omega final, so it's going to come to a stop. What I don't know is how many radians and how long it took. So now let's think about what we have to work with. Whoops. What I want you to do now actually is just pause. Let's kind of dust some of those cobwebs off and see what you come up with. Okay, so when I look at this, I'm thinking, okay, I know my two omegas. I don't know my final alpha, my final theta, but I do know my alpha. So if I look in terms of something like this, where I go, omega squared equals omega naught squared, omega naught squared, let's see, plus 2a, that's at 2 alpha. Instead of delta x, it's going to be my theta final minus my theta initial. Okay, so we're just getting the amount of rotations going through. And then I can look at this and be like, well, that's 0. I know alpha, so I can rewrite this as minus omega naught squared equals, and my alpha is negative, so minus 2 alpha is going to give me my, whoops, times d theta. Will finally get me to my theta. So the two negatives are going to cancel out. I'll end up with omega naught squared divided by 2 alpha equals my d theta. That is the total radians that I've rotated through. So let's see, what do I have? What information do I have? There we go. 18 radians. Oh, I'm not going to do this in my head. Per second squared divided by 2 times 1.9 equals what? Equals something. 18 squared divided by 2 times 1.9. So we get 85.26 radians. Okay, so now I did this without putting in my units. Let's just do a quick unit check over on the side. What do I have? I have radians squared per second squared, and then times alpha. What does that have? That has units of radians per second squared. So because I'm dividing by the radians, ends up on the bottom. Second squared, and I look at this, second squared cancels, that cancels. So I do have just this displacement distance of radians. Cool. So I have that answer. So we know how far does it go? Woo! Okay, let's solve for time, just for funsies. Why not? So we can do that with our delta omega divided by alpha equals time. So my delta omega is just going to be my 18 divided by my 1.9. And it's 18 final minus initial divided by 1.9. 18 divided by 1.9. Whoa, my fingers just went crazy. All right, nope. We go 9.47 seconds. Okay, so now pause. How are we going to get to how far did the coin roll? Pause and come back. Okay, so what did we say? We came back here and we said we have some conversions. There we go. I can go, I know how much time it took. I know what omega is. Ooh. How can I go now to my displacement? Let's see. Do I know the radius? Yes. I was given that. And I know my theta. So wouldn't this just give me my straight up displacement? My distance covered? Because that's just kind of like unrolling that coin. So if you could think of it as like this ball of yarn, this infinite little ball of yarn that's leaving a trail, a straight line trail behind it as it covers these rotations. So x equals theta r. So x equals theta r. So we have what our theta is my 85.26 times my radius, which was what? I didn't write that. Oh yeah, there it is, 0.024 meters. And what do I get? Whoops. 85.2. Okay, that is right. I thought I did a rounding thing. We're good. Times 0.024. So it's gone a total of 2.05 meters. Sweet. Now, you might have noticed one of the things I didn't do here is some sort of conversion from radians to meters. So here is kind of the sad thing, is that radians isn't a unit, but it is something that will haunt you if you don't do conversions from things like rotations per minute to radians per minute. So when we go from our conversion from radians to distance, there's no magic math or anything I need to do to convert my theta into some sort of metery thing. So the long and short of it is, if I'm in radians, once I have that, you can think of it as having kind of getting towards the circumference that we're covering. That's okay. How about that? Just as far as the circumference that we've covered over and over and over and over again, the distance that we've gone is that 2.05 meters. Sorry. I wish I could give you something that would make you happier with that, but make a note, sticky note somewhere. Revolutions per minute or second must convert. Radians to a distance, don't need to. All right, and that's it. Now we're going to do some more new stuff with this.